2 lectures after this. We'll talk about ADMM and then coordinate descent. So here's our case study. This is the problem we're going to study. It's fairly broad because we haven't specified F. And D is also just a generic matrix at this point. And we'll talk about lots of special cases of this. So we're going to consider an optimization problem that's of this form. I'm a statistician by training, so I'm going to use beta as the optimization variable. We minimize f of beta plus some tuning parameter lambda times the L1 norm of the vector d beta. Okay, so f we're going to assume is a smooth and convex function. And d is a fixed matrix that is specified ahead of time. We're just optimizing over beta. And that has m rows and n columns. So this, to some people, may be called a generalized lasso regularization problem. It's like a lasso penalty, like an L1 penalty, but we wedge in a linear transformation. So we're not just taking the L1 norm of the coefficient vector beta itself, but actually a linear transformation of that coefficient vector. Okay, so when D is the identity matrix, suppose that was the specific choice of D that we'd made, that was given to us, then this is just like a lasso penalty, right? And if we had F being least squares lasso, it would just be the lasso problem exactly. So it's a little bit more general than that because we're allowed to transform beta by a linear transformation and then take the L1 norm of that. And so the thing to think of is that this is going to encode sparsity in the elements of the vector d beta. Right? So D is a matrix. We'll call its rows, say D1 through Dm. And if I tell you that D times beta is sparse, that means that I have right, dj times beta is 0 for many j. So another way of saying that is that beta is sparse with respect to this basis, the basis determined by the rows of D. If we say beta is sparse, then that's another way of saying that is it's sparse with respect to the canonical basis. Like if I took D equals the identity matrix, then it's like I had the canonical basis vectors on the rows. So this is just the vectors that have a, for example, Ej has a 1 in the jth component and 0 everywhere else. So if I do Ej transpose beta, and that's sparse, it just tells me that beta j is 0. So being sparse in general, or being sparse without any kind of modification, means just being sparse with respect to the canonical basis. We could think about beta being sparse with respect to a basis determined by the rows of D. And that's what this generalized lasso problem is doing. And depending on what D is, it might yield interesting structure in beta, more so than just having a lot of zeros and some non-zeros. So here are some examples. You guys saw this example on your homework. I mean, an example of this penalty. I can't remember whether we talked about it in class yet, but you at least saw it on your homework. Sometimes we refer to this problem as the fused lasso. If I choose D to have a -1 and a 1 in each row, then saying that D is sparse with respect to these rows means that most pairwise differences of components of beta are 0. Right? So if I take the inner product of beta with these rows, most of them are 0. It just means that beta I plus 1 minus beta I is 0 for most I. Right? So D times beta is the sum of beta I minus beta I plus 1. An absolute value. That's the L1 norm of D times beta. So if I use that as the penalty, instead of enforcing sparsity in beta, it enforces sparsity in d beta, which means that it enforces piecewise constancy in beta. Right? So we'll get this behavior where most of the components of the solution are the same across some range of indices, and then it can jump, and it'll be the same for a while, and then it can jump, etc. So here's an example of this problem in action. I just took some measurements here, right between 0 and I looked at I had 100 points, so I took measurements at indices 0 through 100, and I chose f to be the least squares loss. So that means for every index, I'm fitting a value beta I to the observed value yi, which is this vertical value. And I'm fitting those values beta I to minimize, right, the sum of yi minus beta I squared plus lambda times the sum of the absolute adjacent differences in beta. So what do I get? I get out something that's piecewise constant and that also approximates the sequence y. Okay, so now that I'm remembering, we talked about something similar to this in the first lecture, where instead of constant we had piecewise linear. And you have this on your homework too, this type of penalty. Okay, and we don't have to have y being continuous or f being least squares loss. This is actually exactly like you had in your homework. Here I have binary data, so I observe either zeros or ones. And I'm choosing f to be logistic regression loss. So actually I'm writing them here as z, which means that to every point I'm assigning a probability pi, which is given by e to the beta I over 1 plus e to the beta I. And I'm choosing beta I so that I best match the probabilities to those binary outcomes that I observe. And I want the underlying probabilities to be piecewise constant. In other words, I want the underlying betas to be piecewise constant. So this was another example where I had zeros and ones. If beta is large negative, it means that I'm thinking that it's going to be a small probability. If beta is if beta is positive, then it means I'm thinking I'm going to be observing a large probability. I'm sorry? The red lines. Yeah, the red lines in both plots are the betas, right? If I were to plot the p's here, then they would only be between 0 and 1. But they would look similar too. They'd also would be piecewise constant, because if I have pi equal pi plus 1, that happens only if beta I is equal to beta I plus 1. Okay, so that's just one example. Any other questions? So this was the problem you saw the first class, linear trend filtering. It's like diffuse lasso, but we actually want to enforce not piecewise constancy, but we want to enforce piecewise linearity in the signal, or in the betas. So I do that by putting on the rows of D, instead of just having a -1 and a 1, I have this 1, -2, 1. So that the penalty, the absolute of the L1 norm of d beta, it looks like the sum of overall I of the absolute value of beta I minus 2 beta I plus 1 minus beta I plus 2. And why does this give us piecewise linearity? Well, one way to look at that, which we did in the first lecture, is we said that this is equal to 0, right? The ith term in that sum is equal to 0 if and only if beta I plus 1 is equal to beta I plus beta I plus 2 over 2. Or in other words, if I have beta I sitting here and beta I plus 2 sitting here, then I get a 0 for the ith term that sum if and only if beta I plus 1 is on the line that's joining its neighbors. Right, so if this were a collection of the 3 points beta I plus 1, beta I plus 2, then I'd get a 0 in that term in the sum. So if most of the terms of that sum are 0, then for most triplets, they lie in a line, which means that overall, we'll have these linear stretches, and then at some points, we'll have a change in slope, and that'll just be exactly the values of, say, I plus 1, for which this term is non-zero. So I took this example again. I just had points, yi, I chose least squares loss. I solved this problem for some value of lambda, and it produced for me this piecewise linear function. Okay, so far we've been dealing with just kind of one-dimensional examples in the sense that the input space beta we're thinking has some linear ordering to it. Right here, it was, in both examples, it's ordered from 1 to 100, as if we'd observe it across time or across some underlying variable. but there could be some kind of higher dimensional underlying space, not just the linear ordering. And more generally, we could think that maybe we observe observations for each node on a graph. So let's suppose I have a graph structure that's known, just some predefined graph structure. And at every node, I observe a value of beta. Or sorry, I observe, let's just say, I'm just going to, at every node, I'm going to put down a component, beta I. I don't observe that. That's really what I'm going to solve for. And I may believe that this graph structure defines something over which I would believe the beta should be piecewise constant. So if two betas are joined by an edge, I think maybe they're more likely to have a similar value. So what's the special case of this? If we just had the chain graph, a graph for which I observe nodes 1 through n, and I join nodes 1 to 2, 2 to 3, 3 to 4, etc. That would be this previous situation that we had here, right? Where I just think that being piecewise constant over this graph just means that it's piecewise constant over this line. That's just the special case. But more generally, I may believe that there's some underlying graph structure that gives me some information about the problem. And if I want to fit a coefficient vector beta that's piecewise constant over the edges defined by this graph, then I could do that with the same setup. So I would take D now to be a matrix whose number of rows, so D is going to be m by n. This is the number of nodes in the graph. This is the number of edges in the graph. And every row of D, so D is going to be, again, it's this matrix, right? D1 through Dm. Every row, again, is going to have a -1 and a 1 in it. But now the locations of those -1s and 1s are going to be dictated by the edges. So for example, if I have, let's suppose I were to have the lth edge being ij. If I enumerate the edges and the lth edge joined nodes I and j, so this was say beta I and beta j, then I'll just take the lth row of D to be a vector that's all zeros, except I put a -1 in the ith spot and a 1 in the jth spot. It doesn't really matter whether I put the -1 here or here. I'm taking the absolute value at the end of the day, so the signs don't matter. And so the penalty is going to look like this. D times beta is the sum over all edges, I comma j, of the absolute difference of beta I minus beta j. Okay, so let's look at a very specific example, because you may ask, when would I ever have a graph structure that I can deal with? So here's an example of, these are the states in the US. And what I did was I took the observed number of H1N1 flu cases in the summer of 2009, the proportion of that with respect to the total population in the state. So for every state I have, I observe some value, let's call it yi. It's the number of cases of this flu, the H1N1 flu, divided by, in the state I, divided by the number of people in state I. And that's what I'm plotting. Darker is a larger value of y. It's always between 0 and 1, and darker is closer towards 1. And, well, because the flu is contagious, right, we probably expect that we shouldn't have two radically different estimates of the incidence of flu across neighboring states. I mean, it can happen sometimes, but for the majority of times, because it's contagious, if there was a very high level or there's a low level in one state, its neighbors should roughly reflect this as well. So what we're trying to find, say, is the true probability of getting flu in any one of these states. And we observe noisy observations, which is just observed counts. We think maybe the true probability of getting the flu in each of these states is some piecewise constant function that, as I move from one state to a neighboring state, doesn't jump up a huge level. It's probably constant. So I could, even if I don't believe that to be exactly true, if I believe that that's even a useful approximation, I could run the fused lasso on the graph that's defined by basically the adjacency of these states. So I look at every state. There's 50 or 48 states in the mainland U.S. That is true, right? It's 48 states. I grew up in Canada, so you have to forgive me. So I join any two states by an edge in the graph if they share a border at all. Okay, so I don't remember how many edges there were in this graph, but there are a lot. So I just formed this graph, but it has a -1 and a 1 in each row. And I just ran the fused lasso with a bunch of values of lambda, and I used some held out data as a test set to choose the best value of lambda, and this is the picture that I got. Okay, and so you can see that according to my fused lasso model, which again, you may not believe is exactly true, but even if you believe it's a useful approximation, it's worth looking at. It tells me that the probability of getting the flu is kind of, say, medium for the West Coast states. It's lower for the East Coast states, southern East Coast states. It's medium to low in the Midwest, and then it's particularly bad up here on the East Coast, and I think that's Wisconsin. Okay, so it's a little bit, it's a denoised version of this graph. Okay, this is somewhat of a toy example, but you can see where you would go with this in real applications. So here's another example of a graph. This is another very common example of a graph that we might incur, is just one that's defined by an image. So let's suppose I observe pixels in an image, and it's an n1 by n2 image. And at every value here in this image, I observe a grayscale value between 0 and 1. So then the total number of pixels in the image is n, which is n1 times n2. And if I want to denoise this image, maybe because for various reasons I believe it's a noisy representation of some true image for which a piecewise constant approximation is not a bad idea, I could run the same problem. But now the graph is defined with respect to this image. And what does that mean? Well, if I want it to be piecewise constant over the image, I might say that I'm going to, for this node, I'm going to join an edge between the node north, west, south, and east. So each one of these interior nodes has it joins to 4 of the nodes by edges. So the graph is going to have it's going to have approximately 2 times n edges, because for every point I can just think about joining an edge to the guy to its north and to its east, and that it won't be redundant that way. But it won't be exactly that, because like this guy has no pixel to the right of it, but about that. So this matrix D is formed by, again, just enumerating the edges defined by this image, and it has about 2 times n rows. And if I ran this problem with the grayscale values as the y values and choosing lambda in some way, it'll give me a piecewise constant representation of the image that you pass it. Yeah?
So would there be a difference between imposing sparsity on the edges over sparsity on the cliques?
On the cliques, like?
You encourage a clique in the graph to have the same data. So would this give the same solution?
Like if I are you asking if I added these edges as well? Yeah, so that's going to happen. Those edges will be present. So every edge here is going to be present in the graph. Like that.
So my question was, if the constraints on beta are for each edge, say if you wanted to have a clique in the graph to have the same coefficient for each node, would this give the
Oh, I see. So you're asking, so what this is going to do is it's going to give me a connected component of this graph that is constant, has all the same beta value. So for example, it might choose to assign all of these nodes here. I don't have other colors, but let's just suppose I had a blue pen. It's going to assign all of these to be one color and everything else to be another color. But you're asking actually more than that. Can I just assign, say, a clique to be one color? And can I try to encourage that behavior? That could happen here, right? There's no reason that wouldn't happen because, right, if I this is going to be hard to see, but basically I could still enforce this connected component to be all the same color. So that can happen, and I didn't leave in examples of the image denoising application, but I have a few for which you detect something like this. But it's probably not, there's no difference to the penalty between this and something else that has the same difference between adjacent nodes. So it's not specifically enforcing this behavior. This just comes out of the fact that this is a piecewise constant structure in the graph. So what I'm saying is that the value of this in an area of the same size or the same neighborhood is indifferent to the penalty, right? The penalty treats those the same. So it's not specifically enforcing clique behavior. So that's an interesting question, how you might design a penalty to do that. It would probably involve similar structure. Add more edges. Well, I mean, if you knew ahead of time that there were cliques you wanted to pick up, maybe. But I think generically finding a clique, I'm not sure. Yeah, that's true. If you had cliques ahead of time, you could do that. Good questions. Okay, so these are all examples of problems you could solve in this framework. And we've only looked at least squares loss and logistic regression loss. The problems get more rich as we look at different types of losses. Here's another problem that I wanted to bring up that's an important special case. It's not so obvious. Let's suppose we wanted to just run an equality constrained lasso problem. So this was our problem. Minimize f of beta plus lambda times L1 norm of beta, subject to a times beta is 0, where a is some matrix. So we can actually turn this into the problem form we've just been talking about by reparameterizing. All we do is we write, we've come up with this matrix D whose columns span the null space of A. So that we have the following statement. Beta is equal to D times a vector theta if and only if A beta equals 0. For some theta in R, I guess I'll call it K. K is the dimension of the null space of A. Does this make sense to everybody? Okay. So basically, we've now gotten rid of this constraint because we can solve the problem in terms of theta. Because we know that theta, vectors of the form d theta represent any vector beta that satisfies A beta equals 0. So we go ahead and we just reparameterize the problem to be minimize f of d theta plus the L1 norm of d theta. Right, and since I was just considering the loss to be some smooth function, I can just think of this as some smooth function of theta plus the L1 norm of d theta. So we've reduced the problem now to be solving this minimization problem. Once we have the answer to that problem, we just take our solution to the original problem to be beta hat equals d times theta hat, where theta hat was the solution to this problem. Okay, now what's D going to have? What's the structure of D going to be here? Depends on A, right? So what if A was just an arbitrary matrix? I didn't tell you anything about A whatsoever. Well, let's start off even at a more basic level. How would I find D? If I gave you A, how would I find D? Say in practice, like in R or in MATLAB. SVD, yeah. So I take the SVD of A, and then depending on whether I get a skinny or a fat SVD, basically some columns of V in the SVD are going to give me a null space for a basis for the null space of A. right? But if I stick in a dense matrix into MATLAB or R and I call SVD, I don't get out like a sparse left. I don't get out sparse left and right singular vectors u and v. I just get out generically dense singular vectors. So the basis for the null space that I get out by sticking a dense matrix is going to come back dense generically. So D is just going to be some big dense matrix that I know nothing about. Okay, so this is a pretty practical example of a generalized lasso problem where I won't have a nice structure to D, or at least I won't know if I have a nice structure to D. Okay, so enough about that problem. How do we solve it? That's the point of today's lecture. And going through those special cases were helpful because we're going to actually talk about kind of each one of them in turn after we lay out the algorithms and see which algorithms are appropriate for which of those settings. So that's the problem. Let's go through all the algorithms we know. How about gradient descent? Can we do that here? Plain old gradient. No, why not? Not differentiable. Okay, so the next one we learn is subgradient method. We can do that. We can do it to pretty much anything. We can compute subgradients of this guy. Right, so what's the subgradient of the criterion? Well, it's just a gradient of the loss, because I told you it was smooth and convex, plus, I'm going to use the chain rule now for subgradients of linear transformations. So we had this this chain rule for subgradients, which was that if I gave you a function g of x, which was f of ax plus b, then subgradients of g, of x, were A transpose subgradients of f evaluated at ax plus b. Okay, so you should always remember that one. That one's going to be very useful. It's our version of the chain rule for subgradients. So it's like saying that subgradients of this guy are like lambda times d transpose times some subgradient gamma, where gamma is a subgradient of the L1 norm of x evaluated at x equals d times beta. Okay, so that's the subgradient of the criterion. I just need to take look at the vector d beta, find where it's 0. In those components, I can choose anything between -1 and 1. In the components where it's non-zero, I just choose its sign. I multiply that by d transpose, multiply that by lambda. That gives me the subgradient of this part. And I add to that a gradient of f. Okay, so this is the subgradient method. I repeatedly do, beta is, it gets beta plus this guy, right? Subgradient f of beta plus lambda d transpose gamma. Over and over and over again. So we can apply it to this algorithm. We can apply this algorithm to this problem. The downside, as usual, is that it's slow. These updates are fast, right? They don't involve anything except for matrix multiplication, but it's not going to converge very quickly. And you can, we can see that in various instances of this problem. Okay, and here's a little nicer way to write out the update. This is a linear combination of the rows of D. That's what this is right here. D transpose times gamma is a linear combination of the rows of D. Now remember, gamma was a subgradient of the L1 norm of x evaluated at d beta, and we knew that d beta was going to be sparse at the solution. So that means that many entries of x are going to be 0, which means that a valid subgradient for those components is 0. I could choose it to be anything between -1 and 1, but I could also just take it to be 0, which means that d transpose times gamma can look like the sign of that component of x, which is d beta, times the ith row of d over all I for which d beta in the ith component is non-zero. Because any time that that's 0 in the ith component, I could just take gamma I to be 0. That's a perfectly valid subgradient. So I'm telling you that this matrix multiplication, d transpose times gamma, actually is not a huge matrix multiplication. It can just be done over the rows of d that correspond to components of d beta that are non-zero. So this could be very helpful. We'll return to this. Right, this representation for a subgradient of the L1 norm of d beta. Okay, the next one. We learned generalized gradient descent after that. Right, so yeah, in principle we could apply generalized gradient descent here. What's the prox operator? It's this guy. Right, it's just take the penalty, add on this usual least squares term, 1 over 2t times beta minus c, so minimize this over all z. So unfortunately, this is not an easy prox. Unlike it was for the lasso, which was just soft thresholding, if I gave you a generic d, there's no way to solve this, not in closed form. This is already itself a pretty hard optimization problem. Okay, so it may look like generalized gradient is not generally applicable. If we were lucky, if D had nice structure, it could be the case that this was solvable in closed form. For example, if D was diagonal, then something like soft thresholding is going to hold. It's just soft thresholding at different levels for each component. Okay, but in general, it looks like it's probably not the greatest strategy. Okay, we'll also keep that one running just to remember it, generalized gradient. Okay, the other methods, Newton's method's not going to apply, not differentiable, not even, so certainly not twice differentiable. Not an obvious way to apply like the interior point methods we learned, right? Because there's no constraints, and again, this is not smooth. And we haven't talked about 8mm yet, and we haven't talked about coordinate descent. So among the ones we know, we've pretty much exhausted. It looks like only subgradient and generalized gradient are applicable. So we do what you should always do in any of these cases is we try to look at the dual. Even if you think you know how to solve the primal, it's still helpful to look at the dual. It's never a bad idea. It's just going to maybe waste an hour of your life calculating the dual. So it's always a good idea. And we'll take a break now, but you'll see that the dual is going to give us some room to work with. We're going to have some more algorithms to apply. So I want to finish the lecture off. So I got to ask a good question during the break, which is, how do you know which dual to derive, right? Because there are multiple options usually. And so my answer is kind of cheap, but it's all of them. Just look at all of the duals that you can think of, and some of them will be tractable and some of them will not computationally. So in this case, there's not too many options. I can substitute, when I derive the dual, I have to make a substitution. It's unconstrained, right? That was one of our dual tricks that we learned. So I can substitute in, let's suppose I called z my auxiliary variable, that substitution variable I'm using. I can use z equals d beta or z equals beta. That's it. Nothing else. So depending on which one you choose, you'll see that one dual is more or less tractable, the other is not. And by that I mean that one dual is going to involve just d transpose. The other dual will involve d inverse, or d transpose inverse, or something like dd transpose inverse, or the inverse of some matrix involving d. So generally you don't want to do that, right? You don't want to have to solve a problem where you have to compute a matrix inverse just to begin, especially if d was large. So here's the dual that I got, and I'm going to leave you guys to check this with your dual skills on your own. But I substituted in, so I had this problem, f of beta plus lambda times the L1 arm of d beta, and I substituted in z for d beta. So now this is my problem. Okay, and when I went through the motions, this is what I got at the end. I got my dual problem is to minimize over all vectors u, that's my dual variable. F star, this is the conjugate of f, conjugate function of f. Right, so we learned about those. For a lot of loss functions, we know what their conjugates are in closed form. So f star is that function, it's the conjugate function of minus d transpose u, subject to the constraint that u has infinity norm less than or equal to lambda. So what did this do like at a very high level with the D matrix? So F was smooth. F star is going to be smooth. So what did that do with the D matrix? It took it out of the non-smooth part right? I had this L1 norm of d times beta. That was the non-smooth part, hard to deal with. Like when I wanted to drive the prox, I had to just look at the prox of d times beta and the L1 norm. Took it out of that part and moved it into the smooth part. So in the dual, I have f star of minus d transpose u. This is a pretty general phenomena. If you see when you have linear transformations, if you make these, if you take the duals, you'll see they often switch between where they're applied. Okay, so that means that this problem, I took this D matrix, which was kind of complicating my L1 norm. I couldn't apply, for example, generalized gradient descent, and it moved it into f star. And now I have a constraint on u. The constraint function is non-differentiable. It's still the infinity norm, but there's no linear transformation inside that constraint. It's kind of clarified that the non-differentiable part of this problem. Okay, so another thing to point out is that beta was n-dimensional. U here is going to be m-dimensional, where m is the number of rows of D. So for example, if D had many, many more rows than columns, for example, if I was trying to fuse last one a graph that had way more edges than nodes, then U is going to be the number of the dimension of U is the number of edges. So I'm paying somewhat of a price just to look at the dual because my dual variable could be much higher dimensional than my primal. It's m versus n. Okay, what else do I know about the dual? Well, if I look at the stationarity condition from the KKT conditions, it tells me that the gradient of f at beta hat plus d transpose times u hat is 0. That's what relates beta hat and u hat. Depending on f, this might give me a closed form for beta hat as a function of u. Right? So if f was, for example, least squares loss, then it would. If I solve the dual and I get u hat, I can get beta hat, or I can get x beta hat if the loss was y minus x beta squared in the primal. Okay, so this is a recipe for getting beta hat from u hat in many cases. What else do I know? This also comes from the stationarity condition, this condition here, that the ith component of the dual solution, it's either going to be one of three things. It's going to be lambda when the ith component of d beta is positive. It's going to be minus lambda when the ith component of d beta is negative. And otherwise, it's just something between minus lambda and lambda when the ith component of d beta is 0. So what does that tell us? That tells us that if we ever observe a dual solution that has the property that it's between minus lambda and lambda strictly, then we know that, what do we know about the primal solution? It's on the slide, so you can cheat by just looking over there. It's a 0, right? Because if I had this between minus lambda and lambda, I couldn't have had this being positive or negative because then I would have been told that u was either equal to plus lambda or minus lambda. The only time it can be strictly between these two is if the ith component of d beta was 0. So at a very high level, this also tells us that the sparsity patterns between the dual and the primal are reversed, which means that suppose I was at a value of lambda for which many, many, many components of d beta and the ith component were 0. Then I would expect also to see many values of u strictly between minus lambda and lambda. Okay, and let's make this a little more precise. The general trend, we're going to say that a dual solution is dense or sparse if it's up against that boundary or not. So when it's up against the boundary, when it's equal to plus or minus lambda, right, that's the boundary of the constraint region, then we're going to say that's like what we're calling sparsity in the dual. Because it's kind of nailed down at one value, just like being nailed down at 0. Otherwise, it can float in between those two, and any algorithms we use are just going to have to estimate a value that's in some range between minus lambda and lambda. That's a more difficult task than just pinning it to lambda or minus lambda. So that's kind of like the equivalent of being dense in the dual. So what's the trend? The trend is that for large values of lambda, many components of d beta hat are 0, but many components of u hat are between minus lambda and lambda strictly. And for small values of lambda, many values of d beta hat are non-zero, but many values of u are equal to minus lambda and lambda exactly. So in other words, large lambda is an easier problem for primal algorithms because they are looking for solutions at which d beta is equal to 0 in many components. So there's effectively less parameters they have to estimate, right? Because if many of them are nailed down at 0, then they really only have to find those and then estimate the other ones. But small lambda are generically easier problems for dual algorithms because in that case, many components of the dual solution are at minus lambda and lambda exactly. Okay, so that's a general trend that we also should be aware of. If we're interested in solutions for large lambda, it may be easier for primal algorithms. They may require less iterations. For small lambda, it may be easier for dual algorithms. They may require less iterations. Okay, so those were high-level thoughts about the dual. Let's be more specific. How are we going to solve this dual problem? Let's look at generalized gradient. That's our first one. So that's now tractable, right? Because this prox operator, the prox operator for this problem, is just to minimize least squares subject to an L infinity constraint. And that's just projection onto the L infinity ball. Right, so that's a very simple prox. And each component, if you pass me u and you want to project u onto the L infinity ball, or the set of all z for which z in an infinity norm is less than or equal to lambda, I just take the ith component of u and I see whether it's bigger than lambda. If it is, I move it to lambda. If it's smaller than minus lambda, I move it to minus lambda. Otherwise, I leave it where it is. It's a very easy operation to do. So generalized gradient descent or proximal gradient descent, or projected gradient descent is really what this is, in the dual is very easy. Because we just make a gradient step, and then we apply this prox, which is just squashing it at minus lambda to lambda, or leaving it alone. Okay, here's another one that's, this is like what you did in the homework. We're going to rewrite that L infinity constraint. Right, this is the same thing as saying that I have ui between lambda and minus lambda for each I. And now I'm going to write a log barrier function that it looks like this, right? So instead of minimizing f star of minus t transpose u subject to either one of these constraints, I'm going to add on a log barrier function. And that's going to be phi of mu, or phi of u, excuse me. And I may put I'll put the barrier parameter in front. And phi of u is going to be minus the sum of, right, so this is really two constraints for each I. So I look at log of minus lambda minus ui and log of, that's incorrect, sorry. It should be plus because we need it to be positive, otherwise that's not going to be defined. And this one's going to be lambda minus ui. Okay, so that's my barrier function. And I could solve this problem now, and then I could do some kind of schedule for changing t. That was the barrier method. Alternatively, we could just do 1 Newton step and change t, 1 Newton step and change t. That would be the primal dual interior point method. So either of those we could do here on the dual. Okay, any questions? Okay, so how efficient is this strategy, the interior point method on the dual? Well, let's just look at what the update steps look like. Let's suppose we're going to use Newton's method to solve this problem to high precision and then change t, like we would with the Berry method. That means that we have to do, at every step, we have to take the Hessian of this, take its inverse, multiply it by the gradient, and make a step in that direction. That would be Newton's method for this problem. And okay, so let's call capital F of u the criterion. So basically, I need to know the Hessian of each one of these things and the gradient of each one of these things. And then I take the Hessian inverse the gradient. Okay, so I did some calculations on the slide. We're not going to go through them because I don't have enough time. But when we go, you go through them, they just involve the chain rule. That's all it is, right? There's a d in there. That's just chain rule. This guy, you could just differentiate directly. You get that the Hessian looks like d times the Hessian of f star squared times d transpose plus 1 over t times the Hessian of phi. The Hessian of phi is going to be a diagonal matrix, though, right? Because look, phi is just the sum of functions that involve ui. So there's no, if I take the derivative with respect to ui, then respect to uj, that's going to be 0. So this is a diagonal matrix. And this is d times some matrix we don't know because we haven't specified f times d transpose. Okay, and the gradient doesn't really matter what it is for computational purposes. We can just compute it. It's just like ends up being d times the gradient of f star plus 1 over t times the gradient of phi. Okay, the only difference from the slide and here is that I put the t in front of this part in the slide rather than 1 over t here, but it's the same. Okay, so let's suppose we had f, we could derive f star. It turned out that the Hessian of f star was diagonal also. Then to solve these problems, it would be like d times a diagonal times d transpose plus a diagonal inverse times the gradient. So it's essentially going to boil down to a matrix whose structure is dictated by dd transpose. So if dd transpose is sparse, or it has structure or something, that whole Hessian will have structure. Because all I'm doing is I'm changing its diagonal with these terms. So we'll go back to the problems in a sec, but in a lot of the problems we talked about, dd transpose will be sparse. A lot of them will be structured. So inverting that is not going to be a problem. We can do it very quickly. And that was, this is like what happened on question 3 of the homework. There was a matrix D there that was that matrix with -1 and a 1 in each row, and the Hessian was like this, except in this case we had a specific value for f and f star, and it had the structure of end up just being at the end of the day tri-diagonal. So every row only had 3 non-zero elements, and so you can invert a matrix like that very quickly. You don't have to know how to do it, but MATLAB can invert very quickly, or R can. So as long as you tell it appropriately that it's tri-diagonal, it'll do it for you. Okay, and that makes a huge difference. So I think we mentioned this before, but inverting a dense matrix is like n-cubed operations if it's an n by n matrix. Inverting a banded matrix is like n operations. Okay, so it makes a really, really big difference. It may be the difference between using Berry method or not, whether or not these Newton systems are structured. Okay, so putting it all together, what have we learned? Here's the points we learned. Primal subgradient method, iterations are cheap. All we do is we sum up over the active rows of D, the ones that when we multiply by beta, we have non-zero elements. But the convergence is very slow. Primal generalized gradient, we don't know how to do those iterations. We don't know how to do them generically. They seem expensive for a generic D. Okay, convergence is medium. It'll be better than subgradient method, but not super fast. Dual generalized gradient, the iterations involve projecting onto a box. That's the proxima operator, so it's very efficient. It's very cheap. Convergence is, again, it's kind of medium. The dual Berry method, the Newton iterations, they involve solving these linear systems. That could be expensive or it could be cheap depending on D and depending on F. The convergences can be very fast. So those are like the traits of the algorithms we know. And now let's go back to the examples. Okay, so let's suppose we're looking at this linear trend filtering problem. Remember the one that had it's giving us a piecewise linear solution. And the loss is either least squares loss or it's logistic loss. And I tell you that you're going to produce this solution for somebody who wants to study that plot carefully, the plot of the solution, which means that they want a component, a coefficient vector beta back that's really perfectly piecewise linear, very nearly close to it, which means that I want a very high accuracy to my solution. Because if I return you a vector beta that's just close to the solution but not really, to very high accuracy, then I may not get piecewise linearity. It'll look like little wiggles, right? Because many elements of beta I minus 2 beta I plus 1 plus beta I plus 2 will be close to 0. But they may not be 0 exactly or not to high accuracy. So I'll have like little wiggles in my plot. So now we know the constraints of what we're looking for in the solution, high accuracy. The penalty matrix is this tridiagonal matrix. And the loss is either least squares or logistic. What algorithm do you guys think we should use in this case? We have those 4 algorithms to our disposal. Okay, let's rephrase the accuracy thing. What does this mean in terms of what we've learned? It means that I want a solution to a very, very small tolerance. Like if I tell you I want with an epsilon of the optimal criterion value, the practitioner who's asking us to solve this problem is going to ask for epsilon equals 10 to the minus 9 or something, because they want a really accurate solution. So what's that going to affect at a high level? Number of iterations, right? So we're going to want, keeping that in mind, we're going to want a solution to a very, very small tolerance. So let's go through them. Can I do subgradient method? No, I can't, because I'd probably take like 100,000 iterations to get anything close to 10 to the minus 9, or more, depending on the problem, right? I cannot get very high accurate solutions unless I'm willing to do a ton of iterations. How about the primal generalized gradient? Well, I don't know how to solve the procs. If you guys knew how to solve the procs, I'd be delighted, and you could come tell me after class, and I would give you a chocolate bar. But I don't know how to solve the procs. I'm pretty sure nobody does, so we can't really apply it. Okay, what about dual generalized gradient? We could apply it, right? This involves multiplying by d transpose to get the gradient, then taking that box projection. That's perfectly legitimate. But if we want a very high accuracy solution, still we're going to have to run that for a lot of iterations. So the last was the dual barrier method.
So if it's a squared loss, then that's strongly convex. And if you apply the accelerated dual cross gradient, then that should be 1 by root epsilon. You should get like 10,000 iterations.
So the problem is that in the dual, we'll have to write this out more carefully. What ends up being the loss function is the squared loss whose matrix is d transpose. So it's strongly convex, but its smallest eigenvalue in this case is going to be really, really small because this matrix is pretty ill-conditioned. That's a good question, and I kind of went over that quickly, but I don't want to go into too much detail because we have more examples to talk about. So the last option was the dual barrier method, right? And that was good in the sense that we could achieve high accuracy solutions with very few iterations. That's what we're wanting here. We want a very accurate solution. That seems good. But the drawback was that we had to invert the Hessian in each iteration. And the Hessian had this form, right? It was d f star d transpose. And this thing is always diagonal. Okay, so now I'm going to tell you that for either of these losses, if you were to derive their conjugate and take the Hessian, they would be diagonal. So I'm telling you gradient f star, this is confusing, I'm sorry. The Hessian of f star is diagonal for either of those loss functions I wrote on the paper. So you have to invert that d times the diagonal times D transpose. That's actually pretty fast. Again, this is if you form DD transpose, and if you're not convinced, just after class pull up MATLAB and take this matrix times itself transpose. It'll just be a banded matrix. Its bandwidth will be 5, I think, unless don't quote me on that, but its bandwidth will probably be something like 5. Okay, and so inverting that matrix in MATLAB is going to be very easy. So that means that these iterations will be very cheap as they can get for Newton's method, and we'll only need a few iterations to get to high accuracy. So that's really the way to go for this particular example. Okay, so this is just what we talked about. It's all written down the slides in case you forgot the reasons why. So here is this example from our first lecture. I'm pulling it back up. I took the dual interior point method. I just did 30 iterations. This is the solution I got at one value of lambda. And I ran dual generalized gradient. And I did, what was it, 10,000 iterations? 10,000 iterations. And you can see it's very slow to converge. Eventually, it'll probably give me something piecewise linear, but even after 10,000 iterations, we're pretty far from it. This was a moderately large example. I think there was thousands of points. Okay, it's not very good scale. It's not very good scalability. That for thousands of points, I require tens of thousands of iterations.
Sorry, I think if you accelerated this, you do better. I mean, 10,000 not accelerated doing this, this is like 100 for accelerated.
Yeah. It's possible. I haven't looked at it. It's possible. But I think all of the convergence guarantees for the accelerated methods are identical to those for, in a sense, the constants they depend on are identical to those for the generic generalized gradient methods. So at least in terms of the rate of convergences that we can prove, it's still going to be affected by the conditioning of D. It'll just be one higher order. It'll be 1 over k squared versus 1 over k. But the constant there is still going to depend on the smallest eigenvalue of D, which is going to be very small.
Right, but I mean that if you were able to do this with 10,000 iterations of generalized gradient, that's like 100 iterations of accelerated generalized gradient. And so if you actually did accelerated generalized gradient for 10,000 iterations, then...
Yeah, again, I think it's worth trying. But this isn't even close to what we want, right, even for 10,000 iterations, or for 100 of accelerated version. Okay, so the same story holds if I tell you that you're going to solve those Fuse-Lasso problems over graphs. Because D is going to be structured, and it's going to be sparse. So DD transpose, if MATLAB is being clever about it, it's going to invert that very quickly. Okay, and actually, if you've taken classes from Gary Miller or other people in CS, then you might recognize that DD transpose is very close to what's a graph Laplacian. And so people have very fast solvers for graph Laplacians. Okay, so we're not only in the realm of like banded matrices, but also more general forms of matrices that we can invert very quickly. So those Newton steps are going to be very fast. So here's a special case, though. If I just tell you that I want to solve the simple one-dimensional Fuse-Lasso, that was the very first problem we looked at, where I had this -1 and a 1 in each row, then again, I could do the Newton's method, the Berry method with Newton steps. That's really what we said for all of these types of problems. But for this very special case, if I go back to that proximal operator, it looks like this. And for this one, there is a very, very fast, specialized direct algorithm to solve it. It's the only one of these problems that, Fuse-Lasso problems that I know of that has this fast proximal operator. And so I gave a reference here. It's a very recent paper. It's published this year, but the work is maybe a few years old. It uses dynamic programming to solve this directly, so not to any approximation. And so this is what I actually gave you for the question 5 of the homework, and you could run primal proximal gradient descent, or primal generalized gradient descent. It's really only because of this algorithm. Otherwise, we wouldn't have the prox. Okay, so again, it's always worth looking out for kind of special cases in case it's a simpler implementation, right? So it's worth looking out for that. So here's a comparison I did between just running one iteration of, running one iteration of the dynamic programming proximal operator, so one prox evaluation, versus one solve of a banded linear system. So this was it was like doing DD transpose inverse times a vector B if D was this one diffuse lasso matrix as a function of the problem size. So in red is the cost, the average cost of doing one banded matrix solve. And in blue is the average cost of evaluating the prox operator once. And actually, it's kind of amazing. This proximal operator is even faster than one banded matrix solve. And you can see they're both linear. They both look linear. But the proximal operator is even faster than just a single banded matrix solve. And banded matrix solves are like just about the most optimized of the numerical linear algebra methods, right? Everybody trusts that MATLAB is doing that fast, or BLAST, or whatever else they're calling. So it's competitive. It's worth paying attention to that primal proximal operator. Okay, 2 more examples. Let's suppose I gave you an equality-constrained lasso problem. And that means that the D you got out of it, right, you took the SVD, or you did something to find the null space of D. If the SVD was too expensive, you got an approximate null space of D using other numerical linear algebra methods. But it was this big, dense matrix. It had no structure. And somebody tells you that they want a solution to this equality-constrained lasso problem. And it doesn't need to be terribly accurate. They just need a solution to some degree of accuracy. Then what would you use in this case? Well, let's start with the barrier method. Is the barrier method a good idea? Why is it not a good idea? What's that? The cost of iteration is too much, yeah. I can't really afford one iteration if D is large and dense. It's like inverting a large, dense n by n matrix. It's just not worth it, especially if you don't need a very accurate solution. How about the primal proximal gradient descent? Well, we can't really do that because we don't. If D is generic, I told you, right? We can't solve that proximal operator. Subgradient, maybe, right? It's kind of like our last resort most times. But how about the dual generalized gradient? That's really ideal for this setting. Because all it involves to form gradients is multiplication by D transpose, matrix multiplication. So if that's dense, yeah, it's a pain, but it's not nearly the same as solving a linear system in D transpose. We can still multiply by a large dense matrix. And once I've done that to get the gradient, I just cut it off at minus lambda or lambda on each component, right? That's projecting onto the box. So in this case, dual generalized gradient is really the one you want to go with. Okay, and our last example, let's suppose that D is so dense and so massive that even putting in memory is a problem. So we couldn't even do matrix multiplication by D because let's just suppose it's so cumbersome that operation itself is troublesome. So what can we do at this point? Well, of course, Barry method's out, right? If we can't do matrix multiplication, we can't do linear system solves. I just told you that generalized gradient in the dual is not a good idea because it involves matrix multiplication by D transpose. Forget primal generalized gradient, because of course we can't solve that prox. We can't even do matrix multiplication by D transpose. So subgradient method is kind of like our last resort, but it's actually not a bad idea in this case. And so why is that? Why is subgradient method potentially cheaper than, say, dual generalized gradient? They both, if you go back to the form of subgradient method, they both appear to look like they need D transpose. Right? The subgradients here are like the gradient of f plus lambda times D transpose gamma. And I told you D transpose times the vector was cumbersome. But the subgradient method, it's really this representation that we're really keen about. It's the fact that we can take gamma to be 0 in many coordinates. Right? Because especially if you're looking for a solution that has d beta equal to 0 in many components, then a valid subgradient in the ith component is just to take gamma I equals 0. So that means that d transpose times gamma is really like only few rows of d times gamma. I don't even have to store any of the components, any of the rows of d that correspond to 0 gammas in memory. I could just have a list of ones and zeros that tells me which rows of d are active, correspond to a non-zero subgradient. And I just store those in memory. And so I only do this to compute a subgradient. So this could be a small set S. I keep those few in memory. I look at the sign of d times beta in those components. And this is my subgradient update. Right, so put us back on the last slide. So this is actually not infeasible. We could potentially do this. Of course, it's going to require a lot of clever engineering to manage this stuff, but we could do this at large scale. And it would be slow, and it would take forever to get an accurate solution, but if we wanted something and nothing else was possible, this is a valid option. Did you have a question?
When we start with the first iterations, so say we initialize, beta be 0 or something, the first iterations will still be very, very expensive, right? Because it's unlikely d beta will be 0.
No, beta is 0 then d
Well,
beta.
the first time, but like step 2, you have gradient at 0. So like beta will no longer be sparse at step 2.
So I have a better suggestion like subgradient descent. That subgradient descent is 1 by root d convergence, but stochastic subgradient descent is also 1 by root d convergence. So I would take a random one of those i's and update that. And in expectation you'll get the same convergence rate.
Yeah, so that's usually applied to the loss function, though, right?
You just need your gradient to be unbiased.
But so
You just need your stochastic subgradient of the entire function that you're taking a step in. You just need unbiased estimates of your stochastic subgradient. So you can calculate gradient of f of beta and add a random one of those.
what random one of these?
Yeah, that would be unbiased. Right?
Yeah, that sounds probably like an even cheaper solution. Now, so what Adi was saying was that we just take a random subset of the rows and their subgradients, and we just add that instead of actually doing this faithful subgradient update rule. Right? So this is like subgradient descent. What he's describing is stochastic subgradient descent, which we did not talk about this year. We may talk about in the last lecture. But yeah, that's a really good point. So I also want to give the qualifier that what I'm proposing here is not to be like shipped off to industry and solved with like massive computers. Like there are a lot of very clever ways to make algorithms scalable, and this is like a small pitch for you to take from optimization courses. But the last lecture will probably have one of the instructors for the advanced optimization course next year come give a guest lecture, and the hope is they'll talk about scalable algorithms. Right? So when you start running into problems where you can't fit your data in memory, then the game kind of changes. And you don't apply things like Newton's method. You apply things that are seemingly much more simple, but that involve flavors of like stochastic subgradient descent and stuff like that. So you'll learn more at the end of this course, and if you decide to take some optimization courses, then you'll learn more proper ways to do this.
Also, we might want to mention that the primary using DFI method works well and ADMS works well, which we will.
Primal dual doesn't, yeah. So one other, yeah. Before you head off, so that you come to lecture next week, we'll learn one more method for solving this problem, ADMM, and it's going to work really nicely in various situations. So it's just one more tool for you to use. Okay, have a good weekend.